welcome back to our next e-learning video. Today we're going to look at section 5.5 in Sullivan and Sullivan Pre-Calculus. We're going to examine the properties of logarithms. As we look today, logarithms have some very useful properties that we can use to solve equations, to simplify expressions. Once we get into applications, we're going to use these properties. And a lot of the properties are pretty simple. They can be derived from the definition of logarithms and from our laws of exponents. So our first objective today is that we're going to work with properties of logarithms. That's obviously pretty basic, pretty vague. And the first of many properties we're going to look at is right here. Yeah, I'm going to put my properties in blue boxes today for you to be consistent. This says log base A of 1 equals 0. Now obviously when we look at our base, we know our base needs to be a positive number here, but the logarithm of any base that meets that positive requirement of 1 is always equal to 0. Right? To prove it, I'm going to set log base A of 1 equal to the variable y. I'll make log base A of 1 unknown. And then by the definition of logarithms, I can write that as a to the y power equals 1. If I want to solve this equation, I want both sides to have the same base, so I can write this as a to the y power equals a to the 0 power, since 1 is equivalent to a to the 0. At this point, we know that if two equal powers have equal bases, they have to have equal exponents, so the value of y must be 0. And if I look back at how I started this, letting y equal log base a of 1, substituting that back in shows me that log base a of 1 has to be equal to 0. Go ahead and pause the video, record your first property of logarithms and its proof. Alright, next property of logarithms for us to look at. This one says log base A of A equals 1. In other words, if a logarithm's base and its argument are equal to each other, the value of the logarithm is 1. Again, remember the base has to be positive, the argument has to be positive. Okay? To prove this, I'm going to follow a very similar format to the one above. Let y equal log base A of A. Use the definition of logarithms to rewrite that in an exponential form. If I want to solve an exponential equation, I'd love to write it with two equal powers with two equal bases. So obviously a can be written as a to the first. That's trivial. If two equal powers have equal bases, they have to have equal exponents. So the value of y has to equal 1. And now we can substitute our original assumption back in for y, and we have proven that log base A of A is equal to 1. Again, go ahead and pause the video and record your second property of logarithms and its proof. Alright, continuing on with properties. If you're using the Sullivan and Sullivan Pre-Calculus book, they actually refer to this next property as property number 1. I'm not sure why those first two properties I showed you don't get numbers. Obviously the numbers aren't important, we just use them so we can refer back. They're a matter of convenience. But this is what Sullivan and Sullivan refers to as property number 1. And at first it looks a little complicated. We have an exponential expression on the left where we have the base A raised to a logarithmic power, and the exponent is log base A of m. And this expression a to the log base A of m is in turn equal to m. I know this looks a little complicated. It might make more sense after you've seen the proof. So as we prove it, I'm going to start by defining a function f of x equals a to the x. Now this is our most basic exponential function. If f of x equals a to the x, we've already learned that the inverse of a to the x is log base a to the x. So now I have function f and I have its inverse. Based on our knowledge of inverses, we know that if we form a composition, f of the inverse of f of x, the value of that expression has to be simply x. Now I'm going to do some substitution. First I'll substitute in place of the inverse function based on my given up above here, substituting that into here. And then I'll do a composition of functions, substituting that in place of x in my original function f. This gives us our expression a to the log base a of x is equal to x. Now, when the book gave us our property, they were using the variable m instead of the variable x. Obviously, there's nothing magical about which letter we use. So if I replace x with m in my proof, now I have that proof in the blue box up above. What I hope you saw there is that this left-hand expression is a composition of two inverse functions. We've substituted a logarithmic function into the exponent of an exponential function. And if I do that, and the base of the exponential and the base of the logarithm are equivalent, then the value of the expression is just the argument of the logarithm. Go ahead and pause the video there, record this property and its proof. Our next property that we're going to look at is actually very similar. This says log base a of a to the r power is equal to r. Okay? Sullivan and Sullivan refer to this as property number 2. Again, that's arbitrary. I'd like you to pause the video now and try and use my proof from property 1 above as an example to help you do a proof for property 2 here. Go ahead and pause the video and give it a shot. Alright, I hope you were able to use a composition of functions to prove this. Let's go ahead and look at my proof for this. Okay. As we look at this proof, you can see that again I've defined function f of x as this basic exponential function. Then the logarithmic function is the inverse. When I did my composition of functions this time, you'll notice that the only difference between this and the proof above is the order in which I'm composing. Now I'm going to substitute f of x into the inverse function. F of x was just a to the x, and when I substitute that into the inverse function, I know the value of the expression has to be x. Again, the variables we choose are arbitrary, so I'll replace x with r in order to match the properties variable over here, and we have log base a of a to the r equals r. Both of these two properties rely on our understanding of the composition of inverse functions. If we were going to speak in a very casual language, we'd say that inverse functions undo one another. Going to look at an example next. This is example 2 in the book. We didn't talk example 1, but example 1 was actually shown to you at the beginning of the video. It was just proving the first two properties. Example 2 asks us to simplify these three expressions. So please go ahead, pause the video, and simplify the three expressions here in example 2. You're going to use the properties we just got done proving. Alright, you should be finished simplifying those three expressions. Here are our values. Each of these can be done in a single step, just using the properties that we proved earlier. You can see the composition of inverse functions is present in all of these. In example C, I would remind you that ln is the abbreviation for the natural log, and a natural logarithm is just a logarithm whose base is e. If you remember that, you don't even have to show this middle step here. You can still jump from the given expression to the simplified expression. Again, all three of these rely on the composition of inverse functions. Next property, just continuing with properties of logarithms. Alright, Sullivan and Sullivan refer to this as property 3 in their book. When you look at that property, they do a nice job of describing it verbally as well. On page 310 of their book in the yellow box, they describe this property by saying the log of a product equals the sum of logs. So here's our left hand. The log of a product is equal to the sum of logs. All right, we're going to go ahead and prove that now. So as our proof starts, I'm going to define two arbitrary variables, one for each of these terms on the right-hand expression of my equation in the property. I'm going to let log base a of m be the variable a, and log base a of n be the variable b, using capital letters there. Okay? As I continue the proof, because each of these is a logarithmic equation, I can use the definition of logarithms to rewrite it as an exponential. So these two equations follow from these two equations using the definition of logarithms. Now I'm going to look at the left-hand expression in the original property, log base a of mn. Well, we have just said that we know the values of m and n, and so by substitution I can replace m with a to the capital A power, and I can replace n with a to the capital B power. Continuing with our logarithm, I know that by the properties of exponents that if I multiply two powers with the same base, I can keep the base and just add the two exponents. So you can see how I have simplified inside the parentheses here. Now, this goes back to our composition of inverse functions properties we used earlier. I know the value of this is just a plus b. If I return all the way up to the top, where I defined a and b, I can substitute in my two givens, and you can see that all five of these expressions are equivalent. This was the left-hand expression from the property I'm proving. Oh, I'm sorry, couldn't see the last one. There you go. All five of these are equivalent. Here's the left-hand expression from the property I was proving. All of these are equivalent, including the right-hand expression from the property I was proving. Go ahead, pause the video here, record this property and its proof. All right, next property, when I read Sullivan and Sullivan's description from the book, it says the log of a quotient equals the difference of the logs. Obviously this is somewhat similar to the property we just finished. Here I have the left-hand expression, the logarithm of a quotient. Quotient is the answer when I divide, is equal to the difference of the logarithms. Using the proof that we just finished for property number 3, will you please pause the video and attempt your own proof for property number 4? All right, now that you've had a chance to prove that on your own, let's take a look at my proof. Make sure it's all on the screen this time. You can see that the first 4 steps of my proof are equivalent to the proof above. I've just defined the variables capital A and capital B as logarithms, and then I've rewritten those logarithmic equations in their exponential form using the definition of logarithms. Now I'm going to write the expression that was given on the left-hand side of the property that I'm trying to prove. I'm going to substitute in the values of m and n. Here I'm dividing two powers that have equal bases, so I can keep that base and subtract the exponents. I'm going to return to the properties from the very beginning of this section. Using a composition of inverses, I know the value of this is simply the exponent a subtract b, and then I'm going to substitute in with my givens from the very beginning of the proof with my logarithmic values of a and b. And now you can see that all 5 of these expressions are equivalent. Here's the left hand of the proof of the property that I'm proving. Here's the right hand side, and they're all equivalent. If your proof needs any sort of improvement, go ahead and pause the video again and make sure that you use my proof to improve yours. Alright, continuing with properties just over and over and over. This property, property 5 in Sullivan and Sullivan's book, I've put a star next to. You guys can put stickers next to this and draw hearts and use glitter paint. This is a property that's going to be so important to us. We're going to use it so often. And you'll notice what we've done in this property is we've shown that a logarithm with an exponent in the argument can be rewritten with that exponent as a coefficient on the logarithm. This is an incredibly important property when we're solving equations because it allows me to rewrite exponents as coefficients. Right. In order to prove this one, I'm going to start by defining the capital letter A as log base A of m. So log base A of m I'm just defining as capital A. Then I can use my definition of logarithms to write that in an exponential form. Now I'm going to start my proof. Here's the left-hand side of the property I'm trying to prove. Log base A of the argument m to the r power. Using a substitution, I'm going to replace the m with a to the capital A power. I know this is starting to look a little complicated here. Let's clean it up a little bit. Our argument is now a power raised to another power. By our laws of exponents, we know we can keep that base and multiply the two exponents. So now my argument is lowercase a raised to the power AR with the uppercase A. When I look at this, I hope you guys are starting to now see your composition of inverse functions. You should now see that this is just worth capital A times R. That was our exponent from our logarithm. When I go to this A times R, I'm going to use the commutative property of multiplication and just write those two factors in the opposite order, R times A. And then I'm going to substitute in place of that A all the way back up here with my given. I defined capital A as log base A of m. And you can see this is the left-hand expression of the property that I'm trying to prove. So I end up with 6 equivalent expressions here. All 6 of these are the same value. Started with the left hand of the property I wanted to prove, ended with the right hand. Go ahead, pause the video again, record this property and its proof. All right. Next property we're going to look at, Sullivan and Sullivan's property number 6. This is still on page 310 in their textbook. This property, if you look at it, has 2 equivalent exponential expressions. On the left-hand side, I have a to the r power. On the right-hand side, I have a different base. I have the natural base e with the exponent r times the natural log of a. And we know that the natural log is a logarithm whose base is e. And you can see on my notes here, I don't have a proof for this. I'd like you to pause the video and attempt this proof on your own. After you finish, I'd like you to go to the textbook and examine Sullivan and Sullivan's proof and compare that one to yours and see how well you do reading that one from the textbook. Go ahead and pause the video and do that. All right. That was a lot of properties, and I understand that can be a little bit overwhelming. You may want to make a note card that just has the properties of logarithms on it, not necessarily their proofs, just the properties themselves, the 2 that we didn't number, and then the 6 that we did, and use that as a reference while you're doing your practice until you don't need it anymore. As we continue into our notes, now we're going to start looking at using these properties. So the second objective is to write a logarithmic expression as a sum or difference of logarithms. Okay, so write a logarithmic expression. That's singular. We're going to rewrite that as a sum or difference of logarithms. That's plural. Let's go ahead and see what that looks like. So here's example 3 from the text. Log base a of the quantity x times square root of x squared plus 1. And then they've given us an explicit domain telling us x has to be greater than 0. Remember, that's because our argument must be positive. Our goal is going to be to rewrite this as the sum or difference of logarithms. In the book, the directions also say that we're going to express all powers as factors. And I'll show you what they mean by that. So, we're going to start off by using property 3 that we proved earlier. So I'm going to rewrite, remember, the log of a product equals the sum of the logs. So these are the factors from my argument. X and the square root of x squared plus 1. So that is property 3 at work. And then I'm going to remind you that a radical can be rewritten with a fractional exponent. In this case, I had a square root of this quantity, so that's this quantity raised to the 1/2 power. The reason we do that is because of that sentence in the directions that says express all powers as factors. Remember that property that I told you to write in glitter paint and put stars and stickers and smiley faces around? That's what we're going to do right here. We're going to rewrite this exponent 1/2 as a coefficient on this logarithm. That's where rewrite the power as a factor. Factors are multiplied right here. So we have a logarithm base a of x plus 1/2 times a logarithm base a of the quantity x squared plus 1. We've rewritten our single logarithm as the sum of logarithms. That fifth property, the one with stars and glitter paint, we're going to see frequently. Go ahead and pause the video and make sure you have example 3 in your notes. All right, continuing along, example 4. Same directions. We're going to rewrite this single logarithm as the sum or difference of logarithms. We're also going to express all powers as factors. This logarithm is a natural logarithm. Remember, that means the base is e. This is the natural logarithm of a quotient. And again, they've given us an explicit domain. I'm going to use property number 4. That's the property that says the log of a quotient is equal to the product. The log of a quotient equals the difference of the logarithms. My bad. You can see there's the numerator from my quotient. There's the denominator from my quotient. In this, the numerator's logarithm is always positive. It's the first one we write. The denominator's logarithm is always negative. It's the second one we write. The order does matter there. I'm going to continue through with that fifth property, the one with stars and glitter paint. I'm going to rewrite this exponent as a coefficient on the logarithm. So now I've rewritten the single logarithm as the difference of two logarithms. I've also rewritten all my powers as factors. Actually, I could have pointed out I did that here and here. Go ahead and pause the video. Make sure you're good with example 4. All right, you guys doing all right? I know quite a few properties here. Here's example 5. Directions remain the same yet again. We're going to write this as the sum or difference of logarithms. We're going to express all powers as factors. I'd like you to pause the video and give this one a shot before I show it. All right, so we're going to get to do a couple of things here because we have a quotient, and then within the denominator we have a product. So I will use that fourth property, the log of a quotient equals the difference of logarithms, to rewrite this single logarithm as the difference of two. Okay? Then I'm going to look at this logarithm over here, and if I focus only on this single logarithm, I see it as a product, so I can rewrite that as the sum of two logarithms. That's our property number 3. Common mistake here is to forget the grouping symbols. The reason these grouping symbols are necessary is if in the second step here I'm subtracting the single logarithm and I rewrite that single logarithm as a sum, you've got to subtract the entire sum. In other words, we're going to have to distribute that negative sign, and that's all I've done here. This right here, this negative sign, commonly missed by students who don't use grouping symbols in the step above. Okay? Our last step here, we're going to look to express all powers as factors. So remind yourself that a square root can be rewritten as the quantity raised to the 1/2 power. And then I'm going to take all 3 of those exponents on my arguments and write them as coefficients on the logarithms. The 1/2 from this argument, the 3 from this argument, and the 4 from this argument. That's that fifth property, stars and smiley faces and stickers and glitter pens. Go ahead and pause the video there make sure you have this example finished. All right, you guys are doing a great job. Next objective, we are going to write a logarithmic expression as a single logarithm. If you compare that to objective 2, which we just finished, here I'll even put it back on the screen. In objective 2, we were starting with a single logarithm. Now we're going to end with a single logarithm. So we're essentially going to take the example problems that we just finished, and we're going to write the steps in the reverse order. Okay? So, excuse me for a minute. Sorry about that. Here we have log base a of 7 plus 4 times log base a of 3. And our goal is to write this as a single logarithmic expression. So I'm going to use that all-important fifth property to rewrite this factor 4 as an exponent on the argument of the logarithm. Then I'm going to use my property that tells me the log of a product is equal to the sum of logarithms to take this sum and write it as the product of these two arguments. My last step is just an arithmetic step. I'm going to use the order of operations to clean up 7 times 3 to the 4th. Obviously exponents before multiplying. I end up with log base a of 567. Please pause the video here. Get example 6 into your notes. All right, example 6b. 2/3 the natural log of 8 minus the natural log of the quantity 5 squared subtract 1. Obviously the book's authors are just being silly here with the 5 squared subtract 1. I'm going to begin this with that all-important fifth property, rewriting the coefficient 2/3 on this logarithm as an exponent on the argument. Then I'm going to simplify both arguments. Remember that the 2/3 power means I'm going to cube root my base and then square that cube root. So the cube root of 8 is 2. 2 squared is 4. So my first argument is just 4. My second argument, I told you the book's authors were just being silly there. 5 squared subtract 1 is obviously 24. Next, I'm going to use our fourth property, the one that said the logarithm of a quotient equals the difference of the logarithms. Here I have the difference of the logarithms. I can write that as a quotient. Remember, we talked earlier that numerator comes from the logarithm that's positive, and the denominator comes from the logarithm that's negative. As a final step here, I'm going to simplify my fraction in the argument. 4 over 24 can be simplified to 1/6. So this is the natural log of 1/6. I will let you know that if you check this answer in the textbook, the authors have gone a couple of steps further and written this as -1 times the natural log of 6. I'm happy with either answer. Take a minute and see if you can find out why this expression that I have highlighted is equivalent to -1 times the natural log of 6. Then pause the video and make sure you have part B in your notes. All right, cruising right along. Same directions. We're going to write this expression as a single logarithm. Now you can see right now I have 4 terms, but all 4 terms are logarithms whose base is a. If all of my terms are logarithms with the same base, I'm going to be able to write this as a single logarithm. Why don't you pause the video and attempt this one on your own, and then I'll show you my steps. All right, here we go. I've used the property of logarithms that tells me that the product, a logarithm of a product can be written as the sum of logarithms. So that's how I combine these first two. I'm going to use the exact same property a second time on these two. So I've used the same property twice in a row. Last step, I'm going to now look at my two logarithms being subtracted. I know that the logarithm of a quotient is equal to the difference of logarithms, so here's my logarithm of a quotient. Go ahead and compare my work to yours. Pause the video and make any corrections in your notes that are needed. All right. Just some warnings here for you really quick. Red letters, warnings. Your book's authors use the red letter warning on page 312. These are some common errors that you see people use when they don't fully understand the properties of logarithms, or they don't use the vocabulary correctly with products and sums and quotients and differences. The first common error is sometimes you'll see people do a logarithm of a sum being equal to the sum of logarithms. All right, they almost think it's like the distributive property. This is not the distributive property because there's no multiplication right here. This is an incorrect statement. Okay. Another common error you'll see is sometimes you'll have people write the logarithms, the difference of logarithms as the quotient of logarithms. However, if you think about this for a minute, if this were true, you'd be saying that division is equivalent to subtraction. And there's no way that subtracting two numbers and dividing the exact same two numbers is going to be equivalent every time. Okay? Last one you see here, this is a common mistake with that all-important fifth property that we talked about. You can see it looks like someone has said they're going to rewrite the exponent as a coefficient on a logarithm, but because of the grouping symbols, this exponent is not on the argument, it's on the entire logarithm. This is basically stating that an exponent is equivalent to multiplying, and we know that that's not the same thing. Raising something to the fifth power is not the same as multiplying it by 5. And these are some common errors. Okay. From there, if you want to actually go ahead and pause the video and write those common errors, your red letter warnings, and then after you come back, we'll look at a couple more properties. All right, I know today is like death by properties. That's why I said a note card might be useful. These next two properties I'm going to give you without proof. These two properties are based on the idea that logarithmic functions are one-to-one. You'll notice that the two properties are converses of one another. What we see here is if we have two values that are equal, then a logarithm with the same base of each will also be equal. Many people just read that as saying, you can take a logarithm of both sides of an equation. And they're not wrong. Okay? The converse of that just states if the logarithm of two different arguments are equal, then the arguments themselves had to be equal. Of course, for these properties, remember that our arguments have to be positive numbers and our bases have to be positive numbers. So a, m, and n are positive in all of these situations. Go ahead and pause the video and write down these two properties. All right, you're a half hour in. We're almost done. You guys are doing great. Fourth objective. We're going to evaluate a logarithm whose base is neither 10 nor e. Why do we like base 10 and base e so much? Well, one of the reasons we like them is because they're on our calculator. We've got buttons for a natural log and a common log. Here we're going to evaluate a logarithm whose base is not 10 or e. This is just a logarithm base 2 of 7. Now we've done problems like this before. Remember what this is asking is it's just saying 2 raised to what exponent equals 7. All right, well, think about our answer for a minute. We know the answer's got to be bigger than 2 because 2 raised to the second power is only 4. We also know our answer's got to be smaller than 3 because 2 raised to the third power is equal to 8. So our answer for this is somewhere between 2 and 3. The answer's irrational though, so we're going to have to approximate it. The way we can do that is we can define a variable to be equal to our unknown amount. So we're going to say y is equal to log base 2 of 7. Using the definition of a logarithm, I can rewrite that as 2 to the y power equals 7. Now I'm going to use one of those one-to-one properties we just discussed a second ago, and I'm going to take a natural logarithm of both sides. Now I've arbitrarily chosen the natural logarithm. I could have chosen any base, but I like using base e because it's on my calculator. So now I have a logarithm, all right, natural log of 2 to the y power equals natural log of 7. I'm going to use that all-important fifth property. This is the one that allows me to rewrite the exponent on the argument as a coefficient on the logarithm. And then since I'm trying to find the value of y, I'll simply divide both sides by the natural log of 2, and I have that the value of y equals the natural log of 7 divided by the natural log of 2. Remember that y was defined at the very beginning to be log base 2 of 7, which is the expression I'm trying to simplify. So log base 2 of 7 is the same thing as the natural log of 7 over the natural log of 2. I can do that on my calculator, and this is the approximate value. In the book's directions, they did ask me to approximate to 4 decimal points there. I'll go ahead and show you the calculator screen for that one if you want. So the natural log of 7 divided by the natural log of 2, and you can see that's approximately 2.8074 if we round to 4 decimal points. Go ahead and pause the video. Make sure you have example 7 in your notes. Alright, back from writing example 7, I thought I should also show you that there was a point in that where I told you I arbitrarily chose to use base e. I wanted to show you that I could have also chosen to use a common logarithm. So on my calculator screen, if you see me do the common logarithm of 7 divided by the common logarithm of 2, the approximation is identical. If we extend what we just saw in that example, and instead of using constants 2 and 7, we use variables, what we're able to show is log base a of m is equal to the quotient of 2 separate logarithms using any base you want. So this is log base b. You notice we have changed our base. This is a base we don't want to work with. This is a base we do want to work with. So we call this the change of base formula. The change of base formula is necessary because a lot of calculators only have buttons for base e and base 10. And so we're frequently asked to approximate things by changing the bases from a base that's not on our calculator to a base that is. Right? That's all this note really says here. Because of the logarithm, the common logarithm and natural logarithm buttons on our calculator, in practice, we use this change of base formula above with a base of 10 or a base of e. So here's examples of each of those. All 3 of these blue boxes on your screen are equivalent. This is just showing any base you want. This is showing we generally will choose base 10 or base e. Go ahead and pause your video. Write down your change of base formula. With the change of base formula, we can now approximate values like log base 5 of 89. We can do this much quicker than I did log base 2 of 7 a moment ago. Now that we've talked about our change of base formula, we can just decide to change this from a base we don't want, 5, to a base we do want. And we could choose either base 10 or base e because those are on our calculator. You'll notice I've actually done the problem twice here. Once with common logarithms on the left, once with natural logarithms on the right. And again, simplifying those on my calculator gives me the same approximation. Either of these is approximately 2.7889. If we look back at our original problem, it makes sense that our answer is between 2 and 3. because 5 to the second power is only 25, 5 to the third power is 125, so obviously we need to raise 5 to a number between 2 and 3 if we're going to get 89. Here's part B of example 8. Again, very similar to the ones we've done. We've done log base 2 of 7 and log base 5 of 89. Now we're going to try log base root 2 of root 5. Don't be thrown off with the irrational numbers. Nothing changes in the process. Go ahead and pause the video here. Use the change of base formula to simplify this. All right. I chose to do common logarithms with my change of base formula. You could have chosen natural logarithms. Either way, we're going to get that this is approximately 2.3219. Last objective for today. One more objective, one more example, and we're done. Now we're going to graph a logarithmic function whose base is neither 10 nor e. Okay? In order to do this, we've done this by hand, but now I'm going to show you how we can do this on the calculator. So the last example in the section, example 9, says graph y equals log base 2 of x. Right? Well, my calculator doesn't have a base 2 button, so I'll use a change of base. I've chosen here to use a natural base, so I'm going to write that right-hand expression as the natural log of x divided by the natural log of 2. Now I'm going to go ahead and put this in my calculator so we can see this together. So I'm using the natural logarithm of x divided by the natural logarithm of 2. Okay. To help me take this and put it onto my paper, I'm going to look at the table. I can see that in this table, scoop this up for you. If x is 0, then the logarithm is undefined. We know that makes sense because 0 is not in the domain of the logarithm. And then I have values. If x is 1, 2, 3, 4, I can take as many as I need from my calculator and put those into my table. And then I'm just going to plot those on a coordinate plane. Remember that logarithmic functions have a vertical asymptote, so we've clearly labeled that. If you need to, go ahead and pause the video here to make sure you have this graphing example. Whew. That was a bunch, I know. Almost a 45-minute video. Thanks for sticking with me, guys. I know that we just went through a lot of properties here. I am going to show you the textbook. At the very end of this section, there's a green box that summarizes all of those properties we just mentioned. You might want to make sure that you have all of those properties highlighted in your notes. This is what I mentioned. You put on a note card. You use that note card while you're practicing. And eventually you get to the point where you don't need that note card anymore. All right? Thanks for sticking with me through all this today. I appreciate how hard you guys are working as you're doing your e-learning. You guys are continuing to better yourselves as students and mathematicians. I'm proud of you guys. You guys mean everything in the world to me. Keep working hard and stay healthy.